So now it's the time to move to the fourth speaker. So it's the fourth and last speaker in this session, who's Professor Pedro Camanho, a professor at the Department of Mechanical Engineering at the University of Porto and Portugal since 2014, and currently he is the president of the Associate Laboratory in Energy, Transportation and Aeronautics and the Vice-President of INEGI Institute in Portugal. He will give us a talk on a generation of statistical design allowables of composite laminates using machine learning. So it's machine learning again. And yeah, the mic is for you, Professor Pedro.
So thank you very much. Good afternoon. Salam alaikum. I'd like to thank Gilles for the kind invitation. It's a pleasure to participate in another KAUST workshop, this time remotely. And the purpose of my talk is to describe a methodology to generate composite design allowables using machine learning. So I'd like to acknowledge the contribution of my co-authors, Albertino Arteiro, Martin Salgado, and Luís Pereira from the University of Porto, Carolina Furtado from MIT, Fermino Otero from Sydney in Spain, Rodrigo Tavares from Ghent University, Miguel Bessa from TU Delft, and Giuseppe Catalanotti from the University of Évora. So it's a truly international effort, although all the authors sometimes in their career had a relation with the University of Porto. So this is the outline of my presentation. I'll start with an introduction and also with the motivation for this work. And then I will describe the analytical framework that we use to predict the notch strength of composite laminates. Then I'll move to the design of experiments and the corresponding computational analysis. And then I'll explain how we generate V-basis allowables using machine learning. And with that, I will conclude my presentation. So I'd like to describe some of the important innovation drivers in the aerospace industry. And the first one is, of course, digitalization of processes with the potential to lead to reductions in cost and lead time. So Airbus' goal is 25 reduction of lead time and cost in the design and certification of new aircraft. And if you look at Dakar's vision for 2050, the goal is to reduce the certification costs by 50% in 2050. So that, of course, requires digital twins, end-to-end simulation. Also, uncertainty quantification and measurement is of paramount importance as well. And I'd like to quote a sentence from a keynote presentation given by Michel Fonetot from Airbus back in 2017, where he stated that today's simulations are providing a single result. In front of the authorities, we wish to provide an envelope of uncertainty associated to the results accounting for variations of specimens. And that requires, of course, a large number of computations. Also, in aircraft design, often we have a process of incremental development. So a given design is being challenged, and we need really to optimize as much as possible the composite structures. And that means, again, that we need to have this interaction between structural analysis codes and optimization codes. So in order to tackle these innovation drivers, we have been developing throughout the years robust and validated models, so basically nonlinear finite element models that were used in a number of cases to predict the strength of, for example, open hole tension or compression, bolt adjoint, both for in-plane and pull-through, low velocity impact and compression after impact, low velocity edge impact and compression after edge impact. For example, here, lightning strikes, you can see the damage caused by lightning strike in a composite structure, all the way to the compression after impact of large stiffened panels. Now, the problem with these models is that they are expensive. So they are expensive both from a computational point of view. So these models can take something between 2 hours and 80 hours to provide one result, and also expensive in the sense that we need expert users, so engineers that are trained in computational fracture mechanics which means that these high computational costs may limit the use of models. So our approach to this problem is to use these models that we have developed in the past to generate the data, and then from that data we create surrogate models that then can be used for optimization and for uncertainty quantification and management, because then we can perform a large amount of predictions with a very low cost. But before doing that, we have to answer two main questions, and the questions are: first, how to define a machine learning based approach to predict composite design allowables, and second one is what is the best machine learning algorithm. There are several to choose from to predict composite design allowables. So this is what we'll try to answer in this presentation. And our approach is based on what is called theory-guided machine learning for the generation of surrogate models. So if we plot the relation between data and scientific knowledge, of course, data science models have a huge amount of data available, but they don't require scientific knowledge. And what we have been doing for most of our professional lives is to develop physical models that incorporate a lot of scientific knowledge, but are based in a small amount of data. So what we want to do is really to anchor the data science models with the physical models using theory-guided data science models. And we do that in two ways. So the first one is what I've just mentioned. So the data will be created by robust and validated physical models. But also, when we are developing the machine learning algorithms, we need to make sure that the results are acceptable from a physical point of view. For example, we do not generate data that from a thermodynamic point of view or from a material point of view cannot exist. So this is something that we have to keep in mind. So we anchor the data science models with the physical models. So the approach that we propose is based on three building blocks. So the first one is the design of experiments. So we have to define what are the model descriptors and the corresponding bounds. We have, of course, to perform the sampling. And again, coming back to what I just said, we have, and you'll see this in the presentation, to modify the sampling method to conform to the restrictions of the descriptors, okay? So this is the design of experiments. Then we perform the analysis and we create a database by running analytical models. So like I said, our goal is to be able to do this with the nonlinear finite element models. So what I'll present today is the generation of a database based on a semi-analytical model. So it's not based on finite elements, but because we want to, at this stage, to have a large database that we can quickly generate. So having this database, we can then move on to the machine learning part of the process. So we generate a training set and a testing set. We do a k-fold validation to identify the best hyperparameters of the different machine learning algorithms that we have used. Then we end up with a trained model that we assess comparing with the testing set. So this is the proposed approach, and I will give you some information about the analytical model. So we are going to generate B-basis allowables for composite laminates with notches, okay? So of course we could solve this problem using nonlinear finite elements, but like I said, we're going to use a simplified model that we have developed and validated in the past that is based on finite structure mechanics. So if we take a composite laminate with a notch, and we have a notch geometry that is represented by this parameter lambda, and we introduce this non-dimensional variable gamma. So we predict strength when these coupled criteria, so it's a stress-based criteria and an energy-based criteria, when the system of equations is satisfied. And like I said, we don't need the finite elements to solve this because we can get the stress distribution from Lekninsky, and we can get the stress intensity factors from closed form solutions that are available in the literature for quasi-isotropic laminates. So we can plug in the stress distribution here in the first equation and the stress intensity factor. Then we have material parameters on the right-hand side of these equations, and we can solve the system for the strength. Now, the thing that we have to keep in mind is that when we are using machine learning and we are sampling our design space, we may end up with non-quasi-isotropic laminates, and these solutions are only valid for quasi-isotropic laminates. So one additional step that we had to perform was to determine solutions for the stress intensity factor for non-quasi-isotropic laminates, and this was done recently in collaboration again with Giuseppe Catalanotti, and we have a paper that is in press that shows how we can obtain these solutions for the stress intensity factor for non-quasi-isotropic laminates. So then we need to understand what are the parameters that we're going to use to define the sampling process. And coming back to the finite fraction mechanics equations that you can see here, you can see that we have, of course, the geometry, the hole diameter and the specimen width that are used on the left-hand side of these equations. And we have two material properties. We have the notched strength of the laminate, and we have the fracture toughness of the laminate. And of course, this changes every time we change the layup, okay? So in order to reduce our space of the parameters that define the model, in the past we have developed a method that uses only three material properties. So basically what we do is to use the approach that was initially proposed by Steve Tsai, based on the concept of trace or size modulus, as it's called today. So in the sense that having the Young's modulus in the longitudinal direction, we can obtain the remaining elastic properties, and from the layup then we can obtain the elastic properties of the laminate that we need again to use in these equations. Also from Steve Tsai's work, we used the concept of omni-strain failure envelope to relate the strength of the 0-degree ply to that of a multidirectional laminate. And in the past, we have also developed some methods that relate the fracture toughness associated with a crack that propagates perpendicularly to the fiber direction to the fracture toughness of a multidirectional laminate. So basically, we just need to know the three material properties: fracture toughness, UN, Young's modulus in the fiber direction, and the strength. Again, longitudinal tensile strength in the fiber direction. We need to know the layup, and we need to know these two geometric parameters to feed our model, okay? So, but we have an issue here because the layup, it's something that we have to assess very carefully, because if we consider each ply rotation of a given stacking sequence as an input parameter, we'll have a huge dimensional space that would render machine learning unfeasible, okay? So we need to solve this problem before we use machine learning. So the way that we solve this problem is to consider only two classes of laminates. So the first one is what Steve Tsai named legacy quads. So in the sense that we only use balanced symmetric laminates with only 0, plus or minus 45 and 90-degree fiber orientation angles. And then we use the double-double laminates also proposed by Steve Tsai. So if we do that, we'll see that for the legacy quads, we can use only two lamination parameters, so Xi A1 and 2, to define our laminates, okay? So the other thing that we have to take into account is if we plot the lamination, the normalized Young's modulus with respect to the two lamination parameters, we can see that they are not independent. So we have a region of feasible layups that we need to account for in the sampling process. So if we use the double-double, again, we just have two fiber orientation angles to define our laminate. And again, if we relate the normalized Young's modulus with now the two fiber orientation angles, we can see that our space is symmetric with respect to this diagonal line. So here we have to take into account restrictions, and here we can take advantage of this symmetry. Okay, so then we have to define the parameters that we're going to use in the sampling and then in the machine learning process. And you can see that using finite fraction mechanics, we can predict the strength based on 7 parameters. So Young's modulus, strength, fracture toughness, hole diameter, specimen width, and layup that corresponds to 2 parameters. So for the legacy quads, Xi1 and Xi2, for the double-double, the 2 fiber orientation angles. But we want to do better than this because we still have 7 parameters, and of course that would require a large data set to properly train the model, okay? So we want to optimize this. We want to reduce as much as possible the number of parameters. So what we can do is very simple. We just use Buckingham's pi theorem, and we relate the normalized strength with only 4 parameters. So we are further reducing our sampling space or design space. So then we have to perform the design of experiments. So we have implemented a Sobol sequence using a SCA Python library, and we have here in this table the material, geometric, and laminate bounds. So we have typical values for the relevant material properties. We have defined geometric bounds as well, and then these are the possible ranges that both the lamination parameters and the fiber orientation angles can take. Okay, so regarding the legacy quads, like I said, we have to take into account that we have a feasible region, and we have another problem to solve, is that we have to solve the inverse problem. So we need to identify a layup from the lamination parameters, and that can be done with some very complex optimization algorithms. But what we did was just to generate a database that relates lamination parameters with layups, and we do that once, assuming that we have up to 32 plies, and then we just interrogate the database to relate lamination parameters with layups. Okay. Then we have to take into account the restrictions, because, for example, if we generate these points outside the feasible region, we just ignore these points, okay? And then the points that are inside the feasible region, they need, of course, to match feasible combinations of XC1 and XC2. So if they are within a given distance, we just move to the nearest feasible point, the sampling point, okay? So this is something that we have to take into account in the sampling process. And then we have an input data point with the seven parameters that define the model. So again, the procedure starts by converting the lamination parameters into a layup, assessing the database. Then we use an analytical model to compute the strength and the normalized notch strength. And then we convert the 7-dimensional space into a 4-dimensional space then to train the model, okay? So this is what we do for the legacy quads. And it's a similar procedure for the double-double. But in the double-double, like I said, we can take advantage of this symmetry in the sense that the Sobol points that are generated in this triangle, we just move them to we reflect these points to this region here, which means that we can have a densely populated database here that can be used to train the model. And then the procedure is the same, okay? We get the laminate parameters, convert into a layup, compute the notch strength, and then we convert the spaces. Okay, so we have used four algorithms, Gaussian processes that are well suited for regression problems but are poorly scalable, artificial neural networks that are scalable, able to deal with large data sets but are harder to tune, random forests, and XGBoosts that are fast learning processes, do not require data standardization, and the hyperparameters are easily tuned. So what we did in terms of optimizing the hyperparameters for all the algorithms that we use was to implement this k-fold cross-validation that corresponds of using just the training set and split the training set in k groups. And then for each group, we take one group as the test set, the others are the training set. We fit a model with a given set of hyperparameters to train the set and to evaluate it in the test set that we have previously defined. And then we have an evaluation score, and we rank the hyperparameters, and we repeat this process in the sense that all the groups must be at least once the test set. And we then identify the best hyperparameters. So we do this once to optimize the hyperparameters of all these algorithms, and then we are in conditions to do the final evaluation in the testing set. Okay, we do this evaluation by performing these learning curves. The idea here is that, of course, data is expensive, this data that we have generated is not very expensive because it comes from a semi-analytical model, but if we are performing non-linear finite element models, or if we are using test data, of course, that is expensive. So we want to understand what is the ideal size of the data set, then to generate the V-basis allowable. So, and you can see here the root mean square error related with the number of training points for the different algorithms, both for the legacy quads and double-double. And there are two important observations here, is that for small numbers of training points, Gaussian process outperform all the other algorithms, but when we have large data sets, then artificial neural networks are really the best options. And also another important conclusion is that in our case, we just need 1,000 training points to then move on and generate the V-basis allowables. So the other thing that we did was to represent the design space. So we use 1,000 training points based on the previous conclusion and 9,000 testing points. And we have here for the legacy quads, the relative error obtained by the different algorithms. And you can see that all of them are well within 10% bounds. And we also wanted to see whether these machine learning algorithms can perform properly sensitivity analysis. So what we did, you have here the 7 parameters. So, and what we did was to change the value of, say, Young's modulus, keeping all the others constant. And we see, so this dashed line corresponds to the analytical solution. So this is the ground truth. And you can see that artificial neural networks and Gaussian processes provide a smooth representation of the sensitivity of the different parameters, whereas the other two methods have this irregular representation with these continuous derivatives. So in terms of performance sensitivity analysis, we already identified the best algorithms for this purpose. So in terms of double-double, similar results. So the errors are well within the plus or minus 10% error for all the algorithms. Of course, you can see here that artificial neural networks and Gaussian processes outperform the other algorithms, and the same result here in terms of the sensitivity analysis. Okay, so we can now, having tested our machine learning algorithms, we can then move on and generate P-basis allowables that are used in aircraft design. So just to recall, the P-basis allowable corresponds to the 95% lower confidence bound on the 10th percentile of a specified population. And it's a metric that accounts, of course, for geometric and material variabilities. So to generate P-basis allowables, we have used a Monte Carlo-based approach. So we generate 10,000 material and geometric parameters following a given statistical distribution. So a uniform distribution in terms of the geometric parameters that account for variabilities in machining of machining process, and the normal distribution in terms of material properties. Then we calculate distribution of notches strength using the analytical model and the trained machine learning algorithms. And then we calculate the 10% percentile of the distribution of the notches strength, and we take that as the P-basis value. So for this example, we have used carbon epoxy laminate IM78552 for different hole diameters and different ratios between the hole diameter and specimen width. And then we have used this legacy quad laminate and this double-double laminate. Okay, so and the results are shown here for the legacy quad and for the double-double for the different algorithms. So you can see both the distribution, and here you can see the mean value, and here the dashed line corresponds to the P-basis allowable that is used in aircraft design. And you can see that all the algorithms that we have used perform very well, both in terms of capturing the distribution and, of course, then in terms of capturing the mean value and the P-basis allowable. So with that, we can then move and to propose design charts. For example, if we have a given material, so the legacy quad with the IM78552 and with the layup that we used, or the double-double, again with the same conditions that we have used, so we can, using artificial intelligence, generate design charts that then are used by engineers, both in terms of mean values that correspond to these continuous curves, or based on B basis allowables. And you can see that these design charts, so what we can do here is for this particular material and layup, we can select what is the geometry of our specimen and then predict immediately the notch strength. You can see that the correlation between the analytical model and then the surrogate models is quite good, which really gives us confidence that these machine learning based surrogate models can be used to define these design charts that can be based on B basis allowables. And of course, this is one example for a given material or for a given layup, but we have now the surrogates that can be used for a whole family of materials and layups as well. Okay, so to conclude my talk, I think that I've demonstrated that using analysis models and restrictions in the definition of layups, it is possible to define machine learning models to predict not just strength of composite laminates. We need really to understand these restrictions in terms of the layups and the problems associated with the high dimensional space that we have if we don't use, in this case, either legacy quads or double-double laminates. We've seen that the Gaussian processes achieved best performance for a small number of data points. Artificial neural networks outperform all other algorithms for larger data sets. All machine learning models provided good estimations of B-basis design allowables. Based on our study, we think that Gaussian processes should be deselected and prefer machine learning models. Take into account that first we have a continuous and accurate representation of design space. We do get a low errors in the predictions. We've seen a fast learning process. We have a low number of hyperparameters to optimize, and we have the best performance for small training sets. So if you're interested in this work, you have more information in this paper that was recently accepted for publication in the International Journal of Solids and Structures, where all the details of what I've presented are available. What we are currently doing is to extend this methodology, but with data generated from nonlinear finite element simulations, and that requires some additional studies, but the overall framework shouldn't change. And with that, I'd like to acknowledge the funding from the Portuguese Foundation for Science and Technology, and also all the useful discussions with Steve Tsai from Stanford University. And I'd like to thank you for your attention as well.
Thank you very much, Professor Pedro, for the very interesting talk. We have one question from Professor Gilles Lupinot here. So please go ahead.
Thank you very much, Pedro. Thank you for the nice presentation. I have a question about the overall strategy. Since you analyze a little bit the structure of your data by doing a sub-ball analysis of your system, so you get more ideas about the structure of your data, and can you use this to design or to give a specific structure to your neural network? Because there is probably a correlation between the type of network that you can use and the structure of the data when you make the sub-ball analysis. No?
Well, that's a good point. We tried other sampling processes like Latinite per cube, but what we realized, so we didn't relate the sampling process with the different machine learning algorithms. What we have observed is that the different sampling methods that we use provided the same performance for all the machine learning algorithms. So there was not a clear relation between the performance of machine learning algorithms and the sampling process that we use. So at the end, we in the presentation and also in all the results, we decided to use just the sub-ball as the sampling process. Maybe there's a relation, but for this particular case, we didn't observe any correlation between what is your sampling process and then the machine learning algorithm that we eventually use.
Yeah, what I mean is because because you are using a sub-ball sequence, but you can also, when you have this, you can also define the sub-ball index, that will give you the sensitivity to each parameter.
Right.
Also
Okay.
and it will give you an idea of the depth of the correlation between the parameters. You know, you have the first and the second order and the third order and everything.
Right.
And this gives you an idea of your data. And maybe using this, you can get an idea of what are the kind of layers of structure of your neural network that you need to put in place to represent this correlation between the parameters. What I'm
right. So that's something that definitely is worth exploring in the future. That and also the way that we optimize the hyperparameters, because there are more sophisticated methods. You can actually optimize the way that we select the hyperparameters instead of using this k-fold validation. But what we wanted to do at this moment, so I think the main message is, of course, there are improvements and more information that we can extract from the old methodology in terms of the sampling process, trying to extract additional data in terms of optimizing the hyperparameters. But our main goal here was really to understand the whole framework, and then we can optimize different parts of the framework, including, for example, having the data for other structural details, not only for these notched laminates that we have used.
Thank you, Pedro. Thank you.
Thank you. We still have one question in the Q&A from the audience. Okay, the question says, it's interesting presentation. Could you please comment on how difficult it's to use machine learning for nonlinear finite element models? What difficulties you can think of?
Yes, I think there are two main difficulties that we have to overcome. So the first one, we need to do a sensitivity analysis, because here we have 7 parameters that can be reduced to 4. Okay, so when you're using, depending on your model, you can have, I don't know, up to 20 parameters that define your nonlinear finite element model, because then you may have, you know, in your overall model, you may have cohesive elements, you may have continuum damage model, you can have phase field, so you can have, you know, different models, but for sure you'll end up with more than 7 parameters, right? So you need to perform a sensitivity analysis to see which ones are the ones that, for a given structural detail, are the ones that control the response. Additionally, what I think then we need to do is to use a reduced order model. So we need to use reduced order models to generate the data. Otherwise, it's going to be too time-consuming to generate the data. So these are the 2 main steps that I believe are necessary. So first is to perform sensitivity analysis, and then reduced order modeling. And then we can go ahead and fit the data with the overall procedure that we have proposed here.
Yeah, that's clear. Okay, thank you very much, Professor Pedro.
Okay, thank you for the invitation.
Thank you.